Welcome to Pomodoro Joe for Monday, May 15th, 2023. Today we're looking at LeetCode problem 1721, swapping nodes in a linked list. This is a medium problem. You're given the head of a linked list and an integer k. Return the head of the linked list after swapping the value of the kth node from the beginning and the kth node from the end of the list. The list is one indexed. And then they have an example here, 1, 2, 3, 4, 5, and you're given k is 2, so it's 1, 2, and you swap it with 1, 2. Okay, so you swap the 2 and the 4. Okay, and let's look at our constraints. We have n nodes, but we're not told n in our function, so we'll just have to calculate that. And 1 is less than or equal to k, which is less than or equal to n, which is less than or equal to 10 to the 5th. Okay, so we know our k is less than or equal to n, so that's good. All right. So with this, we'll put 25 minutes on the Pomodoro timer, and we will get started. So I think I'll start with just the basic pieces that we're going to need. So we'll need to know which nodes we're swapping. We'll need to know node 1 and node 2. So I'll just call that n1. And for now, I'll set it to none because we don't know what it is. And n2, also none. So these are the two nodes that we're swapping. The first node, or the kth node from the beginning, and the second node, which is the kth node from the end. Now, when we do the swap, we actually have to reconnect these links here. So we'll need to know the node that came before the node we're swapping, and we'll need to know the node that comes after the node that we're swapping, so we can reconnect these two links. So let's just start with those as well. So I'll call that n1 previous and n1 next, and n2 previous and n2 next. Okay, so these are the basic pieces we need to actually get the nodes and do the swap. Now, how do we get the nodes? Well, my plan here is to just go through our list. So we'll have one other pointer that's just our node pointer. So I'll just create that now. So we'll have a node pointer. That'll start at the head of our list. Now we're going to go through our list from the start to the end. We'll also keep a count. So when we get to count k, we know we're at the kth node from the head of the list. So that finds our first node. Then to find our second node, we'll just start a new trailing pointer. As soon as we reach our kth node, we'll start a trailing pointer and we'll keep going. Then when our leading pointer, or this node pointer, reaches the end of the list, that means our trailing pointer will be at the kth node from the end. You can kind of think of it as like a trailer. So you'll have one pointer sort of tied by a string to the trailing pointer, and as the first pointer advances, it sort of pulls that trailing pointer along. It's always going to be k nodes behind the leading node. So when the leading node gets to the end, that means our trailing node will be at the kth node from the end. All right, so with that, we will create our count here. We'll start at 0, and then we'll say while our count is less than k, then we'll advance our node. So our node is equal to node.next, and our count will increase by 1. So our node is going to start at the head of our list, and we're going to keep moving down the list. So the node equals node.next until our count is equal to k. So this means that our node should be at the kth node at this point. So before we move on, let's just do a quick check. If k is 1, let's say that's sort of our edge case, I guess. It's going to be the very first node. So if k is 1, count is 0, count is less than k, so our node gets advanced to the next node, which will end up at 2 here. So this isn't quite right. I think the problem that we're going to run into is this is a one indexed list. So our count should probably start at 1 because our node is at the first node, which is the head. Now let's try that. Now if k is 1, then our count is not less than k. So we skip this and node will be head, which is right. Now if our k is 2, then count is 1. We'll advance our node to the next node, so it will become 2. Our count advances to 2, then it's equal to k, so it doesn't go through the loop again, and we are at the right nodes. Okay, so this gets us through our list to the right node at count k. So this is just advancing our pointer here. Now, in order to do this properly, though, we'll need to keep track of the node that comes before our node that we're swapping out, because we do need to reconnect that node's next pointer. Okay, so in here, we're not just going to be advancing our node, we'll also be advancing our previous node. So our n1 previous here, well, if we're advancing our node and we're advancing our next node, so what will this be equal? Well, if it's going to be the previous node and we're advancing our node here, well, then this will just be the node itself. Now I'm going to do this a little bit more explicitly. It's a little bit more work, but I think it makes it clearer. So this node is just going to advance through the entire list, just from the head to the end. Our n1 node is the node that we're using to keep track of where our first node is, or the kth node from the beginning. So here we'll advance our n1 node, and that'll be n1.next. And our n1 previous will be n1. So we'll advance n1 to the next node, and we'll keep the previous node, or the current n1, in n1 previous. That does mean, though, that this n1 can't start as none, because there is no none.next. So our n1 here, this will have to be a head. And I think that works out. Let's just make sure that works. So if we have k is equal to 1, this will come in here. It won't do this because 1 isn't less than 1. So our n1 will be the head, and our previous will be none, which is correct. Now if k is 2, then we go through this one time. n1 previous becomes the head of the list, and n1 becomes n1 next, which is 2. And then we break out of this. And I think that's right. Our previous will be the head of the list, and our node 1 will be this 2. Okay, so this will get us to the kth node from the beginning, and it will keep track of the previous node, so we can reconnect this link right here. Okay, now how do we get to the kth node from the end? So for this one, we'll create a trailing pointer. And I'm just going to use n2 as the trailing pointer. So node 2. And we're going to set it equal to the head of our list. So at this point, our current node here will be at the kth node from the beginning. Our n2 node here will be at the head of the list, which is k nodes behind our current node. So now we can just start advancing these nodes together. So we'll advance our current node until it becomes the last node in the list, and we'll advance our n2 node in tandem. And when our current node becomes the last node in the list, then our n2 node will be the kth node from the end of the list. So that's going to get us our second node here. Okay, so the node will be the last node in the list when its next pointer points to none. There are no more nodes. So while the node.next is not equal to none, or not at the end of the list, as soon as that is none, then our node is the last node in the list. So in here, we're just going to be advancing our nodes. So again, we'll do the same thing we did with our n1. We want to keep track of our previous node. So our n2 previous becomes n2. n2 gets advanced to n2 next. And our node, of course, gets advanced to node.next. All right, so this should take us to the end of our list, and then we'll have our n2 previous and our n2. Now at this point, we just need to do the swap. So we'll swap the nodes. All right, we'll need a couple pieces for this swap. We'll still need to know what these next pointers point to. So these next nodes are going to be n1 next is just going to be equal to n1's next, and n2 next is just n2's next. Now you might be asking why we bother storing this. Well, we're going to be reconnecting this n1 next to point to something else, so we need to keep track of where it was pointing before so that we can do the reconnection properly. Now we have all the pieces we need. We have our previous nodes, our current nodes, and our next nodes. So let's just do node 1 first. So node 1's previous node will point to node 2. Node 2's previous node will point to node 1. And now node 2's new next node will be node 1's previous next node, or current next node. And node 1's next node will be node 2's next node. Okay, I know that's confusing, so let's just write it out here. So the node 1 previous, so that's the node that comes before node 1. Well, now it has to point to node 2. So its next will equal node 2. And now that we've reconnected node 2, we've swapped node 2 in for node 1, we need to reconnect node 2's next to point to where node 1 had been pointing. So node 2.next, that's going to equal to n1 next. And now we have to do the same thing for node 1. So node 2's previous will now point to node 1. And then node 1 will now point to node 2's next. Okay, so this should perform the swap. I'll change this around. So this should perform the swap. The node that comes before node 1 previous, its next will now point to node 2. Now node 2's next will now point to what node 1's next was. Then node 2's previous node will now point to node 1. There we go. And node 1's next will now point to what node 2's next was. Okay, so that's swapping out these nodes. Now, one thing that I haven't taken into account, what if these were the head or tail nodes? So this n1 previous could be none. It's certainly possible because it starts as none. So we better make sure that we're not pointing to none here. So let's just say if we have an n1 previous. And this should be okay, because if we don't have an n1 previous, then it means we were at the head here, and we don't need to reconnect anything there in terms of pointing to the head. Same thing down here. Okay, so now that we've taken care of that edge case, I think we're all right. Now the final piece, we still need to do our return. So what do we return? Well, normally we just return the head, because we've just swapped two nodes. We didn't necessarily create a new list. But what if node 1 or node 2 were the head? In that case, we have swapped node 1 and node 2, which means we've swapped the head. So we can just do a quick check. If node 1 is equal to the head, well then we'll just return node 2, because we swapped out node 1 for node 2. And if node 2 is the head, well then we can just return node 1. Because again, we've swapped out node 1 and node 2. Okay, so I think this should do it. We've got all our pieces here. We have the previous, the current, and the next nodes for both node 1 and node 2. We keep track of our current node and our count. We'll go through, find the kth node from the start, and we'll keep track of that in this n1. Along the way, we'll also keep track of the previous node, so n1 previous. Then we'll set a trailing pointer to the head, and while we're not at the end, we will keep advancing our trailing pointer and the node together. So when we get to the end of this, we will have the kth node from the end of our list. Then we'll keep track of the next node. So now we have our true, previous, node, and next for each node 1 and node 2. Now we perform the swap. If we have a previous node, then we'll reconnect the previous node to the next node, and we'll reconnect the next to the swapped nodes next. All right, I'm not going to go through all of this. Then at the very end, we will return, well, if we were swapping n1 and it was the head, then we have to return n2 because that becomes the new head. If we're swapping n2 out and it was the head, then we'll return n1. Otherwise, we just return the head. All right, let's give this a try. And we don't, okay. And we pass one, but we don't pass the other. Let's see what happened here. It says it found a cycle in the list node. All right, and it looks like we're swapping 5. So this is 1, 2, 3, 4, 5. So that's this 7. And then we go back 1, 2, 3, 4, 5. So that's this 8. So we swapped this 7 and 8. Yeah, so that's an edge case that I didn't account for. So this edge case is where the first pointer is actually pointing to the second pointer. which means that when we reconnect this second pointer, so this first pointer is pointing to this second pointer, which is going to be this K1 next. Let's see, where is that? So this N1 next is pointing to N2. So when we reconnect N2, this N2 next, it's going to be pointing to itself. So that is a problem. How do we handle this? Well, we don't want it to point to itself, so let's just check if it's pointing to itself. So that's if N1 next doesn't equal N2. So we can reconnect N2's next to N1 next as long as N1 next doesn't equal N2. Else, well then what do we connect it to? Well, we don't want to connect it to itself, but what do we connect it to? So when we do this swap, this needs to connect to, looks like N1, because N1 gets swapped out for N2. So we'll just say else N1. And we'll have to do the same thing down here. So we can reconnect N1's next if N2 next is not equal to N1, else N2. Now let's try that. And now we pass. Okay, let's see if this does all the test cases. And we pass. We do okay, 42% for runtime and 22% for memory. So now there's a couple things we can do to speed this up. We'll jump back and do this now. So the first thing we can do, this while node.next is not equal none, this is going to have to grab the node and follow the pointer to the next node before it does this comparison. We could, instead of doing this, we could advance this node ahead of time. So in here, if we're setting our N2 to head, what if we advanced our node to the next node already? So now we're one ahead, which means that when the node itself becomes none, then we know we're at the end of the list. So we can change this, which will actually mean that we only have to dereference this one time, and we don't have to do it every time through the loop. So this should actually save us a significant amount of time. Let's try that. Still works. Let's see if it saves us anything with our runtime. And it doesn't. It actually makes it worse. That surprises me. Okay. Well, what else can we do here? I'm actually going to swap this around. There we go. I just think it looks cleaner this way. All right. I think most of this is pretty clean. I'm going to get rid of our comment here just because the more lines it has to parse, the longer it's going to take. So clean that out. We could actually get rid of a lot of this white space, but let's just see if this makes any difference. And we keep getting worse. All right. Okay, the last thing that we can do here, and I was sort of holding this back because I wanted to go through the entire process of swapping out these nodes. You'll notice it does say, return the head of the linked list after swapping the values of the kth node. We don't actually have to reconnect the nodes. We don't have to swap these nodes themselves. We just have to swap the values of the nodes. So what happens if we just swap the values? Well, we still have to find our two nodes, which we've done, but we don't need this previous. We don't need this next. We don't need this previous or next. We'll still do all of this, but we don't need this previous. We don't need this one. Now we don't need any of this stuff because we're not actually swapping the nodes themselves. We just need to swap the values. So we can say n1.val, comma n2.val. This is something Python lets you do. If you're not using Python, you might have to have some temporary variable to hold on to these values. But for Python, we can just say n1val, n2val is equal to n2val, comma n1val. So this will swap our two values, and then we'll return the head. Still works. Let's see if this does any better. It's a huge improvement. We're now at 81% for runtime and 12% for memory. Now there's still some other things we could do in here. So for instance, this N1 next and node next, these are basically the same thing. So we could actually move this out. Let's remove this. And out here, we can say N1 is equal to node. So that saves us a little bit here. And this can start as none because we aren't actually advancing it. Okay, let's see if that does anything. And we're at 97% for runtime and at 22% for memory. So that is a huge win. And this is the best that I'm going to be able to do today. Let's see if you can do better. All right, so that's it for me. This one we go through, we have to find our two nodes. We find the first node by keeping a count, and we find our second node by keeping a trailing pointer. Once we find the two nodes, we can just swap their values and we're done. All right, hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.